So welcome to your first online physical science lab. Hope y'all are all doing well, staying home. I hope you and your families both well, being smart. So this first lab is all about sound waves. We're going to talk about calculating speed of sound. We're going to talk about calculating wavelengths of those sound waves as well. So let me get you into the math and I'll show you how everything's set up. I'm going to be doing the experiment for you. You're going to see all those numbers showing up on canvas, and you're just going to use those numbers to complete your lab handout, answer your questions. Then you're just going to submit that, upload that on Canvas for me. All right, so let me get the camera turned around here and we'll talk about the math. Part one of this experiment goes back into the first couple of chapters talking about speed. So just remember, speed, you're taking the distance an object travels divided it by the time, or in this case we're talking about a wave. And then some of your questions are going to ask you to solve for time. So if you take that formula, you rearrange it, what you're going to have is that time is going to equal the distance divided by the speed. Now in the lab experiment, I'm going to be giving you the time, okay, but we need to talk about this distance right here. So what's going to happen is we're going to generate a sound here in the lab experiment. That sound's going to travel away from that source. In this experiment, it's going to hit a plastic little diaphragm. So that sound travels all the way over here, hits this diaphragm, and then it's going to reflect back, and we're going to have a microphone over here right where the sound was as well. So what you need to keep in mind is that while you might know this distance, or in this experiment you're going to know the length of the tube, you got to think that this sound travels all the way down right here, and then it comes back. So really your distance is going to end up being twice the amount you might think it was right there in the first place. Now as you get into some of your questions, question number one is going to use this equation right here. And this equation, you'll see it on your handout, but it's calculating the speed of sound. And what it's saying over here is that the speed of sound depends on this temperature. If the temperature changes, that's going to change how fast the sound is traveling. So if the temperature were 0, then this whole part right here is going to equal 0. And so if the temperature is 0, the speed of sound is 331.5 meters per second. But I'm going to record the temperature for you here in just a minute as well. And so you need to factor that temperature in. The greater the temperature becomes, the larger T is, the larger the speed of that sound is going to become. Okay, so you're going to see that in question number one when you start comparing your results. And in part two, what we're going to see is that we're looking at calculating the speed of a wave. That the speed of a wave is right here. We're talking about the wavelength times the frequency to give us the speed. Now on your page, it's going to tell you right here to divide by 100. The reason that's there is my measurements are going to be measured in centimeters. The 100 is there so that we can convert those over to meters. And so when we get this speed, it's going to end up being meters per second. Now here's some of this kind of fun sound or music and math and how these things kind of all tie together. In the second part, we're going to have a tube that's open on both ends. And so what happens is a sound wave gets amplified inside of this tube, and at each end of the tube right here, you have an antinode. Okay, so you get antinodes at each end. Right here in the center of the tube, you have a node. And so what that means is when you hear this term, the first harmonic, that means that inside of this tube, right now you have half of a wave. Okay, so at any one moment, you would have, at one moment you might have this part of the wave right here, or the next moment you might have this part right here. So at any one moment, you just have half of a wave at a time. And we're going to use that idea in making some calculations on part two. All right, so let me show you the setup we've got right here. I've got a ring stand, and on this ring stand, I've got a microphone attached to it. That's connected over here to my LabQuest. Now, my LabQuest, let me do this real quick. My LabQuest, I've got it talking to my iPad over here, just so I got a little bit bigger screen for you to be able to capture and see what's going on as I do this experiment. I've got a little dog clicker here. This is going to create our sound. So what's going to happen is the microphone is going to detect this sound that I create. Right? Now this is a long hollow tube right here. Okay, I've got it stretched out. And I've got it stretched out, it's upside down, sorry. I've got it stretched out to right here, 120 centimeters. Okay, so what's going on? I got a second tube over here to show you. Okay, here's what happened. You got this blue plastic diaphragm. As I take this tube and I made the whole thing longer, right, that blue diaphragm is what we were doing here. These numbers are right side up so you can see them. Is as I stretch this thing out more and more and more, now that blue diaphragm is 120 centimeters from this opening. So that sound wave is going to travel down that tube 120 centimeters, and then it's going to come back 120 centimeters. And so let me just do that for you once here. And so I'm pressing collect on my LabQuest. I'm coming over here, generating a sound, and it gives me this waveform. All right, so let me show you what's happening here. You got all these spikes right here at the beginning. That was the microphone detecting the original sound. And then that sound's traveling down the tube, and all of a sudden now you get this next bunch of waves. What this is showing me is this is now the microphone detecting the echo. So the goal here, what we're looking for, is to find how much time passed by before this echo returned to the microphone. Okay, so what I'm trying to do is I'm trying to get my little, I'm trying to do 10 things at once here, but I'm trying to get my little pointer to touch the first time I kind of see a new large spike right here. Okay, that first new large spike, let me come back over here. That's when the echo arrived at the microphone. And so we've got right there, you see the time right down here, 0.0070 seconds. Okay, so that is trial number one. What I'm going to do for you, I'm going to perform this 5 times. Okay, so show you exactly what I'm doing right here. Okay, time number 1, 0.0070 seconds. All right. The temperature of the room, sorry, forgot to tell you that, is 21 degrees Celsius. I took the Fahrenheit temperature that's up here in the corner of the room over here. I took that temperature and I converted it for you is what I've done. But that temperature, again, that temperature is going to be important when you're right down here on number 1 making this calculation. Length of the tube, 1.2 meters. All right, so I'm going to give you these other 4 trials. I'm not going to show you all those. They'll be on Canvas. You're going to calculate the average. Now that you know this average time, and again, really think about the sound's traveling 2.4 meters, then you're going to calculate the speed right here. All right, so give me just a second, and I'm going to get part 2 set up and show you that. Okay, so for part 2, I've got these 3 tuning forks, and I know it's hard to see here, but you got a C, a B, and an A, and you see stamped on them their frequencies. And we got this much, much shorter little tube right here that we're going to be working with. So what I want to do is take one of these, starting with C over here, okay, 512 hertz. I'm going to hit it right here on this rubber, okay, and you can hear that. Right? But when I bring it over here to this tube, that should amplify the sound, but only when I have this tube at the correct length. Let me just take a second here, and I know, sorry about the camera. Okay, and I made this tube a little bit shorter. Okay, so now you still hear the sound, but not quite as well. So what I'm trying to do here, and I can't do it, sorry, holding the camera with one hand and the tuning fork with the other, but what I want to do is adjust this tube until I can make this sound as loud as possible right here. Once I've done that, I want to take and I want to measure how long my tube is. So let me pause for just a second. Okay. So what I did during that pause is I adjusted this tube until when I put this tuning fork here, for it to make as loud a sound as I possibly think it can. Okay, so it's not too long, it's not too short. All right, now I want to measure the length of this tube. So as I set it down here next to my meter stick and zoom in here, let me get you on the right angle, 29.5 centimeters. So as I come over here, the length of this tube for using the C, 29.5 centimeters. Now once I know that length of the tube, again, what's happening here is I have half of a wave inside that tube. So if I want the entire wavelength, what I need to do is take the length that I just measured and really multiply it by 2 right here. Right, so what we're really saying is the length of the tube is half of a wave. We want to get the wave all by itself, so we're multiplying by 2. I'm going to do the same type of thing right here with these other 2 tuning forks, with a B and with an A. I'm going to record those links for you. You'll see those on Canvas, you'll see them in the handout. Right, now you need to calculate the wavelength, right? But again, by what you're doing is you're multiplying by 2. Correction and addition right here. All right, so back here on part 2, I told you to take the length of this tube times 2. Also, you're going to want to add 3.8 centimeters right here, and that's back here. It tells you on number 7 that you need to do that. The reason you're having to do that is just because these 2 cardboard tubes are slightly different size, and that's going to affect the resonance. But we had to have that so that one of them could fit inside the other one and make the whole thing adjustable. But that's the reason for the adding 3.8. Then you want to calculate the speed, right? And so this is where we're using that formula. The speed of a wave equals its wavelength, right, that you would have just found, times its frequency over here. And this is the other part that I pointed out on the board, but right here it is in the handout. You need to divide that by 100 so that you can really get it converted to meters right here. Right? And then you got one box down here on number 2 that you need to calculate for a different frequency. You have the speed of the sound. So if you know the frequency and the speed, I want you to calculate the wavelength and then figure out for me what's the first harmonic, the second harmonic, the third harmonic. You'll see those other harmonics over here back on page 4, kind of how all that math ties together. And let me point out one other thing right here on question number 1. Question number 1 asked you about the frequency versus the length of these tuning forks. All right, so look at these carefully. Again, here's a C with a frequency of 512. Here's a B with a frequency of 480. Here's an A with a frequency of 426.7. So highest frequency, lowest frequency. That question number 1 on part 2 is asking how does that compare to the length of these tines right here. All right, so I hope that kind of made a little bit of sense, hopefully. But if not, look, feel free, reach out to me. If you got questions, concerns, you're stuck on something, I'm here to help you. So let me help you if you need it. All right, y'all take care, and I will talk to you again soon.